Okay, then let's start the final installment of Fundamentals of Optical Coherence Tomography. It's lecture 5, actually, final installment. And last time, in the last moment of the last lecture, I explained I'm going to talk about the applications of the OCT today. But today, actually, I'm going to talk about the applications of, say, hot extensions of the OCT. Okay, so it's not an application of the standard OCT. Today, I'm going to introduce a recently developed functional extension of OCT. It is so-called as Jones matrix OCT, and its applications for the ophthalmology. Okay, there are two new points today. One is a new extension, functional extension. It's Jones matrix OCT, and then applications of the optical coherence tomography. Particularly on this Jones matrix OCT I'm going to show today is data taken by my own research group, computational optics group at the University of Tsukuba, COG. Okay, so then let's get started. So today's main topic is Jones matrix optical coherence tomography and its applications, as I've explained. The Jones matrix OCT is one of the keywords. I'm going to explain about it later. And also, the application to eye imaging is one of the biggest application or one of the most important application of optical coherence tomography. But anyway, let me start from the technology-wise, the Jones matrix OCT. Okay, the Jones matrix OCT is an extension of polarization sensitive OCT. So then, what is a polarization sensitive OCT? Or sometimes we call it as a PSOCT in short. Okay, the polarization OCT by a single scan gives us, in addition to conventional standard optical coherence tomography image, gives the polarization property of the tissue. Okay, the conventional OCT is based on the scattering property of the tissue, whereas the polarization or sensitive OCT gives us a phase retardation and a birefringence information. Technically, there are several other parameters associated with the polarization of the tissue. But anyway, we can obtain the polarization properties, it's plural, of the tissues, okay? Let me show some history of PSOCT. The first demonstration of PSOCT was done by the group of Massachusetts General Hospital, Johannes de Boer, Professor Johannes de Boer, okay? And then in 2002, the same group applied this technique for the posterior eye retinal imaging. Okay, and 2004, the group in Vienna demonstrated the first high-speed retinal OCT imaging. 2002, that was a little bit slow on that time, but at 2004, it becomes quite high speed. Okay, these are the breakthroughs of early polarization sensitive OCT. And Jones matrix OCT then is a further extension of the polarization sensitive OCT. We have been working for more than 10 years. The first time we were working for the polarization sensitive OCT, but then we started to generalize that technology and finally integrate anything into this theoretical framework. And this is so-called as a Jones matrix OCT. Okay, the basic conception of the Jones matrix OCT is detecting the most general representation of the optical property of the tissue. Actually, this is a time sequence of Jones matrix of the sample. Okay, maybe you student of Institute of Physics already know about the Jones matrix, right? But maybe you've learned that the Jones matrix is a polarization matrix. Means it's a quantity expressing the polarization property of the sample or material. But in reality, Jones matrix is not only the polarization property or polarization quantity. It possesses anything about the optical property of the tissue except the real depolarization, physical depolarization. Okay? In addition, by taking the time sequence, we also can include that, for example, Doppler shift or something. It's a temporal fluctuation property of the tissue also can be encoded into the time sequence of the Jones matrix. So now anything except the real depolarization, real physical depolarization except, can be encoded into the Jones matrix sequence. And then the conception of the Jones matrix OCT is measure the three-dimensional distribution of the time sequence of the Jones matrix. Okay, there is the time sequence of the Jones matrix. It's a one-dimensional property along the time axis, and each Jones matrix has 4 entries, 4 complex entries. Okay, so there are 8 parameters. The 4 times 2, real and imaginary. But in reality, phase is only relative. So there is 7 degrees of freedom. And then times, the number of freedom is times the time points, number of time points. So in our cases, frequently we take 4. Okay? So then that is for each single point, spatial point of the tissue. And we take it in a 3 dimension. It's a kind of huge data. But the point is, the Jones matrix is a kind of mathematical quantity, mathematical and purely physical quantity. So it might be out of interest of the clinicians who are the main user of OCT. But the point is, Jones matrix possesses anything about the optical property of the tissue. Okay, and once we measure it, we can derive clinically useful features by applying the proper mathematical operators, mathematical or say numerical operators. That's a conception of the Jones matrix. Measure the most generalized quantity and then derive a specific quantity afterwards, after detection. Actually, this is the initial conception of our current research of the computational augmented optical coherence tomography. But in any way, this one is a kind of very early demonstration. Okay, so then now we have the Jones matrix. I'm going to talk about how we can measure the Jones matrix of the sample later. But assume we have the Jones matrix, okay? And then by applying, for example, coherence composition algorithm, we can have a high sensitive scattering OCT image, okay? And then from this, even we can derive the local scattering or local attenuation coefficient imaging. This is tightly associated with the density of the tissue. It's a microscopic information of the tissue, and its size is smaller than the resolution of OCT. Okay, and then by applying the phase analysis along the time, we can measure the Doppler shift of the probe beam. It encodes the flow speed in the tissue, especially of the blood flow. Okay, and similarly, we also can compute the temporal correlation of the time sequence of the signal, and it gives us the flow contrast. Okay, the Doppler OCT is a quantitative flow. And this flow contrast based on the correlation analysis gives us more subjective representation of the flow. Maybe qualitative is better word. Qualitative representation of the flow. And from this, for example, we can obtain a label-free non-invasive angiography, so-called as OCT angiography. Okay? And in addition, surely the Jones matrix possesses the polarization information, maybe as you've learned in undergraduate school. By applying the eigenvalue analysis or eigenvalue decomposition, we can compute a phase retardation or local phase retardation, so-called as birefringence. And for the clinical application, birefringence is known to be specific for the collagen or other microfiber structures, like the nerve fibers. And especially for eye, what we are interested in the nerve fiber and the collagen. Okay, but in any way, by using this trick, we can have a kind of molecular specificity. Still weak, but have molecular specificity. Okay. In addition, we can compute something similar to depolarization. Okay. As I mentioned, we cannot measure the depolarization by using Jones matrix. Jones matrix is a coherent matrix. So anything coherent, the coherent phenomenon can be captured by the Jones matrix or represented by the Jones matrix. But the Jones matrix cannot represent a reduction of the coherence. The depolarization is a reduction of the coherence. So technically speaking, we cannot present the depolarization by using the Jones matrix. But if the physical depolarization occurs, most probably the randomization of the polarization states in a small tissue region occurs. Okay, there is a kind of the physical relationship and a practical physical relationship between the real physical depolarization and the polarization, spatial polarization randomization. And we can measure the spatial polarization randomization and can treat it as a kind of alternative of depolarization. And this is so-called as degree of polarization uniformity in its original definition. Or sometimes we call it as, in short, the polarization uniformity. Okay? So the polarization uniformity is still a kind of physical quantity, but the important point is this is specific for melanin. For standard tissue, the polarization uniformity is quite high. But once the tissue has the melanin, it induces the multiple scattering of the photon. And it results in a degradation of the uniformity, of the polarization uniformity of the tissue. Okay, so by measuring the polarization uniformity and finding out a region with a low polarization uniformity, we can visualize the three-dimensional melanin distribution of the tissue. So again, we can have some kind of, say, molecular specificity, three-dimensionally and even label-free. Okay, the conception of the Jones matrix OCT, and still it's growing and growing. But at the basement framework, or basement conception, the Jones matrix OCT is measure the most general quantity and derive anything after the acquisition. It's a way of thinking. Okay, it's kind of my style. Having a general representation and a specified layer is actually my very basement attitude for anything. Okay, so then maybe your next question is how we can measure the Jones matrix. And for this, we introduce two hardware tricks to that optical coherence tomography. Here it's an example of the swept source optical coherence tomography. The Jones matrix optical coherence tomography. So here is the light source, the sweeping light source. Maybe in this lecture, I'm mainly concentrating on the spectral domain OCT. But this specific implementation of the Jones matrix OCT is based on a swept source OCT. The spectral domain OCT and a swept source OCT are something similar. But a spectral domain OCT, as you've learned, measure the spectrally resolved interference signal by using the spectrometer. Means using the broadband light source, and when it is going to be detected, we resolved it into the wavelength spectrum. But a swept source OCT is not. It uses a scanning laser. At a single time instance, it's lasing a single wavelength. Okay, but this lasing wavelength scans quite rapidly, like 100 kilo repetition along the time, right? So then the detector itself is not a spectrometer, but the balance flow detector. So we can resolve, again, we can take the interference signal in a wavelength resolution manner. And then we can reconstruct the OCT. The mathematical principle of the FD-OCT, the spectral domain OCT and the swept source OCT are quite similar. But implementation-wise, it's slightly different. And by some reasons, for the Jones matrix OCT, we prefer to use the swept source OCT. Historically, we also did it the spectral domain version. But anyway, at this moment, we are mainly working with the swept source. Okay, so here is a swept source OCT scheme, and the light source is here, and the sample is here, right? The eye. And then here is a detector. And we actually introduced two tricks to this swept source. One is a polarization diversification. Okay, the light is coming from the light source, ignore this first, and then illuminate the sample. And backscattered, the light is backscattered and reflected and collected through this coupler and introduced into this polarization detection, diversity detection unit. Polarization, sorry, I say again, the polarization diversity detection. Okay, and the other portion of the beam is split by this coupler and delayed, properly delayed, and introduced again into this polarization diversity detection. Now clean up in its polarization state, and these two beams are combined by this non-polarization beam splitter here. So this means this one is an interferometer. Now we have the interference between this one reference arm in reality and this one probe beam. Okay, and we have two interference signals here and here, and these two are something. Technically speaking, I've explained it once. But it is something similar to, it is for the balance for detection. So we have two interference signals, and the phase of the interference signals is ordered in pi. So that the peak becomes valley, and the valley becomes peak. By subtracting these two signals, we can achieve the high sensitivity detection. It's a balance for detection, right? And this BPD is for this balanced photo detector. We have two. Before doing the balance for detection, we put beam splitters here again. It's PBS, polarization beam splitter. So this means after making the interference signal, this interference beam is split into horizontal and vertical polarizations. And then, for example, horizontal polarizations are combined and detected by the BPD, and the vertical polarizations forms other combination and detected by the BPD, these two. So this means by using this polarization diverse detection scheme, we can have two, say, OCT interference signals. Okay, and by processing it, we are going to have OCT signal. And but it corresponds to different output polarizations. Okay, and then the next trick is this passive polarization delay unit. We frequently call it as a PPDU, passive polarization delay unit. And it is in the probe arm, okay? A beam is coming from the light source and going to the probe arm and enters to this polarization, the passive polarization delay unit, and then passing through it illuminates the sample. Okay, then what the passive polarization delay unit does. Okay, let's see a little bit detailed scheme here. The light, as I've explained, is coming from the light source. Okay, and its polarization is cleaned up by this polarizer into 45 degrees. Then polarization beam splitter, PBS, and it splits the beam into P and S components. Okay, or say, but by some reasons, here I use the P and S, but you also can take it as a H and B, horizontal and vertical. Okay, and then the light is split into P and S components and reflected by these two dark prisms, and then combined again by this PBS, and then introduced into the sample. So this polarization, a passive polarization delay unit, actually split the beam into two and combined again. That's it. That's nothing. However, by using this configuration, we can apply a particular delay into one of the polarization components. Okay, split the beam into two, and it propagates, and one is delayed to the others, mutually delayed, and then combined. So this means you are going to have two beams in a time sequence now. Okay, one is P and the other is S. And this is used for the OCT detection as a probe beam. So this means we have two OCT signals in different depths in the image because of this delay. And one of the image corresponds to P polarization, P instant polarization, and the other corresponds to S instant polarization. Okay, by using this trick, we have two images. And then after this trick, we measure the signal by using this the polarization diversification. Okay, by summarizing it, we can understand what is happening here. Okay, now we have horizontal and vertical detectors. It's a polarization diversification units work. Okay, and here in the depth in the image, we have OCT signal here, right? And this one is a mirror image. Just reminded the theory I've explained in the earlier lectures, right? This one is an OCT signal, and this one is a complex conjugate artifact. Okay. And we have one from a single detector, H, horizontal, for example, and the other from the vertical detector, B. Okay. And it seems there are 4 OCT signals, but in reality, it's only 2. This one is just an artifact or mirror of this signal. Okay. In addition, we use the passive polarization delay unit. So we have the delayed copy of this signal. But technically speaking, this is not only the copy, but associated with a different instant polarization to the sample. Okay, now we have combination of 4 OCT signals by a single scan. Okay, this combination, this combination, and this combination are associated with a different detection or output polarization. And this combination and this combination are associated with different instant polarization, right? So it's a combination of 2 instant polarizations and 2 output polarizations. 2 by 2, it becomes 4. Okay. In addition, the OCT is a complex signal, as I've earlier talked in this lecture, okay, as the Jones matrix is. So technically speaking, roughly speaking, these 4 complex OCT signals form the Jones matrix. Okay, so see a little bit mathematics. Assume this one is a Jones matrix to be measured. Okay, first we eliminate a sample with the horizontal polarization. It's an instant polarization. Maybe P polarization. We denote it as a P polarization in this notation. And in a Jones vector, it is called, it is denoted as 1, 0, right? It's pretty much depend on the definition, but here we define it as 1, 0. Okay, the sample, or technically speaking, it's not a pure sample, but a sample with some optical fiber effect or something. But you can assume at this moment, this is a sample Jones matrix. Okay, and this is illuminated by the P polarization 1, 0. And then what is the output? It becomes like this, right? J11 and a J21. And this guy are actually the output polarization. So this guy is associated with one of the polarization, one of the balance for detector. And this one is associated with a different, another polarization, the balance for detector, BPD. Okay, so means by using the polarization diverse detection, we can obtain this signal and this signal independently. By using that hardware scheme I've explained, now we can measure these 2. Okay, and then we have another instant polarization. It's delayed, S. It is 0, 1 in a Jones vector. By multiplying it, we have J12 and a J22 component, these 2, right? For with the first probe beam, we have J11 and a J21, this combination. Now with the second delayed instant polarization, we have this combination, J12 and a J22. Okay, by combining it, we actually can measure this Jones matrix. The trick of the Jones matrix OCT, and we do we do this measurement in a time sequence manner, typically 4 times, with something like a time spacing of 10 milliseconds or something, 10 milli to 20 milliseconds. And we have a time sequence. And by applying the time sequential analysis, we also can obtain, for example, flow information. I've already talked about it. Okay, so and if you're interested in, maybe you can check on several papers we published, and also there is a textbook chapter I wrote. Okay, but anyway, the details can be found in a textbook or review paper, and I and Johannes de Boer and Christoph Hitzenberger co-authored in a Biomedical Optics Express 2017. But anyway, if you're interested in, please check these references. Okay, so then Jones matrix OCT, the principle is okay. And then what the research activity, hot topics. And technically speaking, it's not really a hot topic. And recently we translate this technology into not for the eye, but for the microscopy. But as a first step to explain for the students, and I just a little bit talked about something like a little bit old story about 2-3 years ago. Okay, so in my research group, we are comprehensively working for the topics, the several layers of the topics of the Jones matrix OCT. It includes, for example, the Jones matrix basement Jones matrix OCT theory. I briefly explained it, but there are a lot of fine details of the mathematics in reality. Okay, and based on this, we can think about the highly accurate Jones matrix measurement method. It includes something like a mathematical estimator or probabilistic estimators, or some algorithm to extract the local phase retardation and a cumulative phase retardation and a degree of polarization uniformity measurement and a noise correction and blah, blah, blah. Okay, and it's a theoretical part. And then we are also working for the instrumentation. It includes the posterior eye imaging and anterior eye imaging and skin imaging, and also recently optical coherence microscopy. Okay, maybe some of the students here already know about it, like a transport system. It's already been published. The several papers have been published with this system. Okay, and then we are also working for some applications, like for the eye imaging, the macular disease imaging and the glaucoma imaging. Okay, and also some types of the chronic disease, like VKH, Vogt-Koyanagi-Harada disease. And then in addition, we are also working for the specific multi-contrast image processing. Okay, the Jones matrix OCT can provide us a really high dimensional signals or images. Now, dimension means that in a feature dimension. Okay, in a single pixel consists of a 5-6 contrast. It's a really high dimensional information. We need to properly design, newly design the signal and the image processing method for this kind of, say, set of images or high dimensional images. We call it as a high dimensional image. And we are also working for this. And then based on it, by using that mathematical framework, we are also working for that medical image processing. It's really a huge, say, field of the research. But today, I'm going to talk about, say, some portion of it, and especially these applications. Okay? So then, the applications of the Jones matrix OCT, posterior eye imaging. So for the posterior eye Jones matrix OCT, what we want to achieve is a comprehensive level-free OCT angiography. Okay, so then maybe on the first thing we need to think about is what is comprehensive OCT angiography? By the way, this is a very important attitude to do research, and especially for not only the student, but also the researchers. When you start the research project, and maybe some of you are given some research topic from your supervisor. The first thing you need to do is to think about what is this topic. Okay, the research topic is not always or very frequently non-self-evident. Okay. The research topic is very frequently non-self-evident. You need to think about what is this research topic. And actually, this is not the passive understanding. You need to build the conception itself. Okay. So in our case, we are starting from the Jones matrix OCT, and I started to think about the comprehensive OCT angiography. So the first step to work for the comprehensive OCT angiography, what we need to do is to think about or to define, technically speaking, to define what the comprehensive OCT angiography is. To think about it, I've started from thinking about a conventional angiographies, fluorescent angiography, FA, and incident green angiography, ICGA. And then we can start. We can think about what these conventional and say conventional invasive angiography do. Which kind of information we can obtain these conventional angiographies? For example, on what we measured with them are circulation and the vasculature of the posterior eye. In addition, the clinician check the tissue abnormality. Okay, so angiography is in its name, looks like watching the vasculature. Okay, it's angiography. But in reality, what we are watching is not only the vasculature, but also the tissue abnormality. In addition, on the vasculature has two meanings. One is a quantitative circulation, and the other is a vascular structure. And the vascular abnormality, the shape abnormality of the vasculature, we need to carefully examine it. Okay, examine the conception. In addition to the tissue abnormality, FA, especially FA, is good for the detection of the integrity of the retinal pigment epithelium. Okay. So then these four informations are the information we measured by using conventional angiography. To achieve comprehensive label-free angiography by using OCT, we need to achieve the imaging of these four properties. Okay, so the question is whether it is possible or not. And surely the answer is yes. For example, Doppler OCT can measure the circulation. And OCT angiography in a conventional meaning. The old classical OCT angiography, it's classical, but still it's only 10 years old. But OCT angiography can give us the vasculature information, but the vasculature structure abnormality information. The tissue abnormality can be measured by using polarization sensitive OCT. Okay, so the point is, by using the several extensions, plural again, OCT, we can measure each of the information. But for this, we need several OCT devices. But by using the conception of Jones matrix OCT, we can unify them. Okay. So then we build a unified posterior eye imaging Jones matrix OCT system. Our first generation is built in 2012 to 2013. Okay. We call it as a shortcake OCT system, the first prototype. The center wavelength probing is a 1.06 microns, and the measurement speed is the same with the current one, 100,000 A lines per second. It results in a volumetric measurement time of 6.6 seconds per volume, and the depth resolution is 6.5 microns in tissue. Okay, these specs are the same with the current one after 10 years. But its utility has dramatically been improved. One of milestone is this 2005 system. We call it the Ceratophrys 1. Anything packed in a box, and also this scanning head. And the point is, this system is workable in a clinic without operation engineers. So this means someone who are not trained for the OCT development can operate it. So this means this system can be stably work in the eye clinic, and it has been working in reality. And we took several clinical data. Even now, we have a next generation of this Ceratophrys 1 and also next generation of this device. And they are working in a clinic at this moment. And this Ceratophrys 1 itself has already been retired. And we retrieved it back into our optics lab and now used for that test implementation platform or new function, new measurement functions. Okay, it's a second life of him already. Okay, and then by using this system, we made it a lot of collaboration with the clinicians and did doing some of clinical studies. And by using it from these clinical studies, I would like to show some of, say, catchy image demonstrations. The first demonstration is a three-dimensional flow and a retinal pigment epithelium imaging of polypoidal choroidal vasculopathy, PCV. It's one type of age-related macular degeneration. Okay, so here is a color fundus photo of the patient. And we see a huge hemorrhage, U-shaped hemorrhage here. Okay, and by checking this eye using inciting green angiography, in its early phase, we again can see this U-shaped hemorrhage. But in by surrounded by this U-shaped hemorrhage, we can see a hypofluorescent region. Okay, and but here we can see a kind of spot hyper appearance of ICG fluorescence. Okay, in a late phase, it becomes large. It is actually the indicator of leakage, dye leakage. So there is an abnormal tissue abnormality. And then by checking this eye by using a fundus autofluorescence imaging, we see the absence of the retinal pigment epithelium, RP damage. Okay, so then my question is whether these informations obtained by three types of conventional devices, even one of it was an invasive method, whether these information can be obtained by using a single scan of the Jones matrix OCT. Okay, and surely the answer is yes. So here is the three-dimensional reconstruction of this case. It's a kind of fly-through on a three-dimensional volume rendering. So evidently, you can see a dome-shaped elevation of the retinal pigment epithelium. And here, the grayscale particles represent the scattering property of the tissue. Okay, it's a standard OCT. And then the gold particles represent the flow that was on that time extracted by using the Doppler OCT information. And the green is a melanin. Technically speaking, it's a retinal pigment epithelium obtained by the polarization uniformity. Okay, and we combine all of this information obtained from the Jones matrix OCT into a single volume. Okay, so there is an elevation of the retinal pigment epithelium, and we can see the abnormal vasculature on top. Okay, and surely this is the elevation of the retinal pigment epithelium because it's green, right? I mean that low degree of polarization uniformity. It's a melanin signature. But on top, there is no green. There is no green signal, melanin signal. So this means this part of the retinal pigment epithelium, melanin pigment, has already been gone. It's the tissue itself is totally abnormal, not only its shape. And here, the situation becomes severer and severer. There is a very huge abnormal vasculature, and on top, melanin has been gone again. Okay, by reconstructing this information into the three-dimensional on volume rendering, we can have more intuitive understanding of this pathology. Okay, let me show it again. So here it's a standard OCT, removing the structure information, and now we see the vasculature in yellow and the RP in green. Okay. So here is the vasculature and the abnormal vessels here, right? And this one is a feeder vessel. The nutrients of this abnormal vessel was fed by this path. Okay, see it again. Abnormal vessels here, and there is a feeder vessel. Okay, by removing it, we see now only the retinal pigment epithelium. This one is, by the way, shadow. It's not normal, but there is a retinal pigment epithelium still. This guy is abnormal absence of the retinal pigment epithelium. It's RP damage. So these informations was something what the clinicians want to measure. And now we can measure it by a single scan of the Jones matrix OCT. Okay. Then let's see a little bit more cases. Collagen property. So far, I demonstrated the scattering imaging is a standard OCT, and the vasculature imaging by using a Doppler OCT and also OCT angiography, on temporal correlation of the signal. And also RPE or pigment imaging by using the polarization uniformity, by using the polarization uniformity. Then we also can do the collagen property imaging by using the phase retardation birefringence imaging. And its main application is scleral imaging. And especially it is useful for myopic cases. Okay, myopia is maybe you thought it's some of the students maybe, I guess you believe myopia is a disease of the lens of the cornea or lens or the cornea. But in reality, myopia is characterized by abnormal elongation of the eye. Okay, so it's a disease of the entire eye globe. And then this stretching or the elongation of the eye globe may be occurred by the abnormality of the exoskeleton of the eye. And the exoskeleton of the eye is a white part of the eye that a collagen structure, we call it a sclera. It's a collagen structure, and it supports the mechanical property of the eye. So the sclera is a white part of the eye, and it supports the mechanical property. And if there is a tissue abnormality of that exoskeleton of the eye, we have the abnormal elongation of the eye, and it results in a myopia. Okay, so most of the cases, myopia is just a mild disease. What you need is only the eyeglasses. But not a small number of them started to have a very continuous development of the myopia. And finally, it reaches we call it a pathologic myopia. You are going to have some kind of tumor in the retina. Okay, it's so-called as a myopic choroidal neovascularization, myopic CNV. By measuring the myopic CNV cases, we are by using the Jones matrix OCT, we can observe something we couldn't see by using conventional method. Okay, here is the retina cross section of the OCT. So there is a choroidal neovascularization here, right? Here is the RPE. But the structure itself might be, the tissue itself is not that much self-evident. But here we see that the retina pigment epithelium, right? By turning on that polarization uniformity, we can identify where melanin exists. Okay, what important here is here in this standard OCT, scattering OCT, we see the retina pigment epithelium. Well, at least we had believed we saw the retinal pigment epithelium. But by turning on the melanin signature, we can see that there is no melanin at the right-hand side. The tissue has already been damaged. Okay? By turning on the birefringence imaging, we see a moderate birefringence in the sclera here, right? The green. That has already been known. But by watching it, we again can find another layer here. It's a low birefringence, blue. The high, again, green, and low blue. Okay. This four-layer appearance of sclera is one of the characteristic property we found in this study for that pathologic myopia cases. Okay, and there is a kind of abnormal thickening of sclera, and it appeared in the second layer of this. By zooming up this layer, we very clearly see that we very clearly see the 4 layers here, and also here we see a very strong birefringence red, and this is actually on. We believe it might be the extension of dura mater from the optic nerve head to the sclera. Dura mater is a kind of capsule of the brain, and it's connected to the eye, and it is actually a very high dense collagen. Okay, and dura mater is normally exists around the optic nerve head, but by the elongation of the eye, it is stretched into the macular position, and we believe we are watching it. Okay, it's a very high birefringence, means a very high density of the collagen. And also again, sorry, maybe I just mistook the order here, the 4 layers, the order of explanation. I mistook the order of explanation. So there is a 4 layers here, okay? Okay, so then again, we started the continued development and reaching to the point of pigment and the simultaneous pigment and flow imaging, or we call it a PATH. The kind of the signal processing with the Jones matrix OCT. So by a single scan of the Jones matrix OCT, we can obtain multiple contrasts, as I've already explained. Now, one of the useful contrasts is OCT angiography, the volumetric data, like this one, right? And also we have a polarization uniformity. It is sensitive to melanin, okay? The melanin is important to visualize the retinal pigment epithelium. And a retinal pigment epithelium is a very aggressive cell, and it plays a quite important role to maintain the retinal function. And surely the OCT vessels are important, right? So these two information, we would like something like we would like to really carefully examine. In addition, we would like to see that the relationship between these two information. So it's worth to combine it, okay? For combining it, what we did is using OCTA as a pixel brightness and using the polarization uniformity. And from the polarization uniformity, we computed the cumulative polarization uniformity from the top to the bottom, right? It's a cumulativity from the top to some particular depth. We sum all of the melanin signature, okay? And I use it as a color information, color hue of the pixels, and combine it. And we are going to have this kind of colorful 3-dimensional volume. And doing a kind of volume rendering as to watch this volume from the top. Okay, by watching this volume from the top, we can have this enhanced image. Okay, so as you can see, there is this one is a normal retina, and as you can see, there is a blood vessel here, and there is another blood vessel. Okay, these are blood vessel in hot colors, like a yellow to red, is a retinal blood vessel. It is appeared as yellow because there is no melanin on top, right? It's above the retinal pigment epithelium. Now for this, we assign the hot colors. And if there is a melanin on top, the blood vessel appeared with blue, cold colors. It's our definition of the color map. But the existence of the melanin was detected by using the polarization uniformity. Okay. So now we can distinguish the retinal vessels and the vessels beneath the retinal pigment epithelium, namely the choroidal vessels. Okay, and if there is an intact retinal pigment epithelium, the retinal vessels appear with hot color, and the choroidal vessel should appear with cold colors, blue. But in the case of pathologic eye, this rule cannot be applied, surely. That's something we would like to see. Okay, here is a case of age-related macular degeneration. In a color fundus photo, we have some abnormality. It's maybe if you are not trained for this, it's a little bit hard to see, but still there is some abnormality. Okay, this is actually another point. If you are not trained, it's hard to find it, but by checking it with the Jones matrix OCT-based Path-OCT, it is quite evident there is abnormal vessel. Surely this is abnormal because of its structure. Okay, and even this is appeared with orange color, means the retinal pigment epithelium on top of it has already been gone. Okay, by zooming it up, even we see some blue signature here. But this means there is a residual melanin at this point. Okay, and this kind of finding can be found by a single glance of the in-face image. But you can double check it with the cross sections. Okay, by checking the cross section at this point, we see these two, right? This one is a combination of OCT blue and OCTA red. Okay, there is an abnormal elevation of the tissue here, and there is the blood flow at this point. Okay, so there is an abnormal vessel in this. There is a hyperscattering cluster, and on the right of it, in the right part of that hyperscattering cluster, we have a blood vessel. It's abnormal. In addition, at this point, we don't have a melanin signature, but in the left part of this abnormal hyperscattering, we have an accumulation of melanin. That is something we are observing. Okay. The melanin accumulation, this one. And in addition, here, there is a less melanin signature at the retinal pigment epithelium. Okay, in the OCT scattering, there still is the retinal pigment epithelium, or at least it looks like that the retinal pigment epithelium exists here. But by checking the melanin signature, the tissue has already been damaged. And in an in-face image, by watching it, then watching the in-face image, we see that the choroidal blood vessels appear with orange. So this means, okay, let's go back. Even this point, okay, that the melanin of the retinal pigment epithelium has already been gone. Means the retinal pigment epithelium has already been damaged. Okay, this information can be obtained by a single scan of the joint matrix OCT and even by the single glance of this in-face image. Okay. Then let's see some other cases. It's another age-related, it's the same age-related macular degeneration, but we did intravitreal ranibizumab injection treatment three times. And after the third time, after 2 months of the third time, we scan the same eye again. Okay, as you can see here, most of the severe disease has already been cured. And this can be double checked by the cross section. There is still a small elevation of the retinal pigment epithelium. But the point is here, all of the blood vessels beneath the retinal pigment epithelium and even the melanin signature recovered here, right? So actually, we can double check it without any labels or invasiveness. Okay. Okay, and then we decided to bring this technology into more and more clinic. We built a specialized prototype which can obtain the path imaging. We call it as a Dendro system. The simplified version of the joint matrix. It cannot measure the full joint matrix, but it can measure the polarization uniformity and the OCT and the OCTA. Okay. By using it, we started to do a higher dimensional contrast generation. Okay, so now there is a Jones matrix OCT conception, and we can have the primary contrast. And then we started to combine these primary contrasts to derive a tissue-specific contrast. Okay. So then, why did we start to work for this? Okay, the issue we want to solve is this one. Jones matrix actually gives the optical contrast, not the tissue contrast. But are ophthalmologists really interested in optical contrast? Okay, in reality, it's not. they are interested in tissue contrast, not the optical contrast. It's a kind of huge misagreement, hidden misagreement, tacit misagreement between our engineers and the ophthalmologists. Okay, and then how we can solve it? We can we can sensitize the contrast by combining multiple optical contrasts. It's a contrast synthesis, the conception of the contrast synthesis. So for example, by using it, we can contrast the retinal pigment epithelium originated melanin. Okay, for this, it's just one example. Okay, let's explain the concept first. We have we have multiple optical contrasts obtained from the Jones matrix OCT. And we can combine it, and we can generate the intermediate contrast. Sorry, it's not a combination. From these direct optical contrasts, we can manipulate it, and we can create an intermediate contrast. And then combining it, and then we can have a synthetic tissue feature contrast. Now it's a tissue contrast. What we can do, it's an example of the melanin associated with retinal pigment epithelium imaging. What we are going to use is a scattering OCT and a polarization uniformity and OCT-A. Okay, from OCT, we computed the attenuation coefficient of the signal. It is associated with the density of the tissue. And from polarization uniformity, we computed the polarization diversity. It's a 1 minus DOPU, defined as. And then from OCT-A, we can segment out non-perfusion area. It's a binarized OCT-A signal, a binarized signal of 1 minus OCT-A with this equation, right? And then multiplying them. By this multiplication, we can selectively contrast the melanin associated with the retinal pigment epithelium, RP melanin, okay? And then by applying a threshold, we can very easily segment out the retinal pigment epithelium. So here the point is, this segmentation doesn't utilize any morphological information. So this means even the severely diseased eye with a severe deformation of the retinal pigment epithelium, we can generally apply this method to segment out the retinal pigment epithelium. Okay, so then by using it, we can find for example, visualize the detachment of pigment epithelium, PED, pigment epithelial detachment. Here is the case in OCT. There is a very severe detachment of the retinal pigment epithelium, and I computed the attenuation coefficient DOPU and perfusion pixels. Now from this, we surely can compute the non-perfusion pixels, right? By combine, From this OCT image, we see a hyperpenetration here, right? Abnormal high signal. This is actually the indicator of the retinal pigment epithelium damage, but it's not seen, clearly seen in OCT. But by checking the polarization uniformity image, we see a clear damage of the retinal pigment epithelium. Okay, so all of the information, all of these information can be combined by using the contrast synthesis framework. Okay, and by combining it, for example, we can obtain the melanin, RPE originated melanin contrast here, and there is a RP damage. It's quite clear. And also we developed another algorithm to contrast the choroidal stroma. By combining it, we have this kind of image. Here's an OCT, the choroidal stroma overlaid here as a green, and RP originated retinal, and the RP originated melanin appear in red. Okay, and even this algorithm can be applied for the three-dimensional data, and we see the three-dimensional pathologic structure. Okay, that is something like the final part. On that time, at least, the final part of the project, starting from the basement theory and doing the instrumentation and building the clinical device, and developing a signal processing and applying it for the clinical study, and then working for the multi-dimensional contrast signal processing and image processing. Okay. So then, to close today's lecture, I would like to show one case of retinal pigment epithelium, melanin, and a near-infrared FAF, fundus autofluorescence image comparison. The near-infrared fundus fluorescence is a method which can contrast the melanin of the retina. Okay, so on our method and the FAF should correspond to each other. Should correspond to each other, right? And here the left is the near-infrared fundus autofluorescence at the wavelength of 788 nanometers. Okay, and here is our RP melanin thickness map created by that algorithm. Right, and both of them are M-fast. In FAF image, we see a kind of segment of the melanin, RP here. It's abnormal, and we see a very clear pattern correspondence of these hyper FAF and RP melanin accumulation. Especially this guy has really a similar pattern in both images. But in addition to this, by using this Jones matrix OCT-based method, we can double check the three-dimensional structure, whereas FAF is only for two-dimensional investigation. Okay, so here we can see the RP thickening. So this means the origin of this hyper FAF is this RP thickening, retinal pigment epithelium thickening. Okay, and here we see another hyper appearance. Okay, this is this one, hyper-reflective foci. Means from the FAF, we see several abnormal hyperfluorescence. But by using Jones matrix, we can identify the source of these appearances. So this means this method can be utilized for the three-dimensional version of near-infrared fundus autofluorescence imaging. So, so far I was talking about only the Jones matrix OCT, but it's just the last slide of today's lecture. But recently I started to talk about the entire framework which can comprehend the measurement itself, the activity of the measurement itself. So now the OCT is measuring the tissue, right? So here is our point. But in any way, by observing what the OCT is measuring, the starting point, the disease, okay? There is a disease, and it results in a tissue abnormality, and it alters the tissue optical property. By using the photo-tissue interaction, the interference, we are going to have the interference signal, right? And we detect it and digitize it. By processing it, we have an OCT image. And from this OCT image, we can apply, to this OCT image, we can apply the image processing, this or signal processing. And by using it, we can have a highly accurate OCT image. We call it a true OCT image, like a noise reduction, for example. And then from this, as I've explained, we can have a tissue contrast. And from this tissue contrast image, this tissue contrast image can be fed to, for example, AI for the diagnosis. We have a diagnosis score. Okay, so now anything is in a clinic now. But then what this device, entire OCT device measure, what does OCT measure now? Okay, actually, OCT measure the disease, and the disease is not a substance or even the physical existence. It's just a conception, right? So this means the current measurement system measure the concept. That's something we didn't clearly aware now, and something we need to start to think about. And I call it as an epistemological measurement science or cognitive measurement science. Okay, so so far when I was a student, I thought I was working for the interferometer. It's just a very straightforward measurement. Okay, then but starting making this interferometer into the OCT, I started aware we are measuring the say biological structure. And then I started the signal processing. I started to think about it. I'm measuring the tissue. And finally, we are reaching the point of measuring the conception, disease. that is a kind of new frontier of the measurement science, cognitive measurement science, or say science as epistemology. And that is something I want you guys, young guys, to think about. It's a totally a new frontier of the measurement. And by using this point of view, we can comprehend anything in cutting edge technologies. But making it as a research, we need a clear framework to comprehend anything. Okay, so let me close today's lecture. Today's lecture was dedicated for hot topic of the OCT, so-called Jones matrix OCT. I explained the brief conception and technical background of its implementation. I applied it for the retina imaging, okay? And in short, the retinal pigment epithelium abnormality can be visualized by the polarization uniformity, and a vasculature abnormality can be visualized by OCT angiography. And a birefringence imaging can reveal the previously unknown structures in deep posterior eye. In addition, the multi-contrast image processing enables the tissue contrast, direct tissue contrast by using Jones matrix OCT. And the project itself is still ongoing. Maybe you can expect more and more interesting results in the future. Okay, so then this is the end of the 5 installments of a lecture series of fundamentals of OCT. Okay, so then maybe from the next time, I'm going to talk about a little bit different topics, maybe how we can read the papers or something. But anyway, this is the end of the technical part of this year's lecture. Okay, and if you have any questions, please contact me later. Okay, so it's about a time. So let me close the lecture. Okay, thank you.